So please welcome Jim Al-Khalili.
Excellent. Thanks very much for that. Well, good afternoon, everyone. So, a bit of hard science to entertain you for the next three-quarters of an hour or so. This is a talk which I guess I've given over the years to a range of age groups, and coming up this morning, I have a whole array of PowerPoint files which I look over and swap things around, try and keep things nice and fresh. So the nature of time is something that has been debated by scientists, theologians, philosophers, great minds over the past few millennia. What is time? How fast does it flow? One wag, I think, once said, time goes by at the rate of 1 second every second. Which is a bloody stupid thing to say, of course, and you can't measure something against itself. But our sort of common sense view of time is one in which it's one that we inherited from Isaac Newton, basically. It's one in which we imagine there's this cosmic clock that ticks by the seconds, minutes, the hours, the days, the years at the same rate for everyone. And we know our subjective view of how fast time goes by is not something we can always trust. If you enjoy this lecture, it'll go by quickly. If you're bored, it'll drag. I mean, we know that. But we sort of assume there is this time, some cosmic time that goes by at the same rate for everyone. We also now know that, of course, that view of time is flawed. That view of time as separate from space and our universe is not the way we see things now in modern physics. I also want to touch upon the issue, since I'm going to be talking about time and the past and the future, I want to touch on the issue of determinism. The idea that if, in principle, we could know the position and state of motion of all the bits, the building blocks of the universe, we knew all the forces between all the particles, the atoms and the particles that make up the atoms, if we knew what everything was doing and where everything was in the universe at a given moment in time, then this view of time that we inherited from Newton tells us that we should in principle be able to compute how the future will evolve. That's what I mean by deterministic universe. It's what we call the Newtonian clockwork universe. And of course, since our bodies are only, our brains are made of atoms, particles, physical entities subject to the same laws of nature as anything else, then in principle, knowing the future means knowing what our actions will be in the future. So determinism tends to suggest, and this is a deep philosophical issue, though I don't want to get into too deeply, but determinism suggests that the future is preordained, that we have no free will. Well, this was compounded, I guess, by the turn of the 20th century when Einstein developed his theories of relativity. In Newtonian mechanics, we have the idea that fixing the initial conditions, say in a game of pool, will tell us we'll be able to compute how the future will evolve. Now, of course, we know now there's something called chaos theory, which I won't talk about, you'll be relieved to know, in this lecture, which suggests that we can never know to sort of infinite accuracy exactly where every ball is, so that we can crank the handle of the equations to work out what's happening in the future. Because it's just impossible, the slightest change in temperature or humidity or a grain of dust somewhere would eventually magnify and alter the future. This is what's called the butterfly effect. But it doesn't rule out this notion of determinism, that in principle, were we able to know, then the future is fixed. In 1905, Einstein published a number of papers which revolutionized physics. He proved that theoretically that atoms exist. He described the nature of light as being made of particles. But most famously, he came up with his special theory of relativity. Now, for most people, non-scientists, when you say, what do you know about relativity theory? Oh, E equals mc squared. A lot of people know what the E and the M and the C stand for. But actually, E equals mc squared is boring. It was even an afterthought as far as Einstein was concerned. It didn't even appear in his first paper on the electrodynamics of moving bodies in 1905. What was really profound about Einstein's special theory of relativity is that it gives us this new picture of space and time. Einstein said that there isn't this cosmic clock that goes by at the same rate for everyone. Space isn't just the stage on which things happen. Space and time are part of the fabric, the structure of the universe itself, which means we have, to some extent, some control over space and time. Or indeed, we have different perspectives, different views on distances in space and intervals, durations of time. Well, what does this mean? It leads to this notion of what's called the block universe. Now, we know we live in 3 dimensions of space, right? I can move forwards, backwards, left, right, up and down. All solid objects in our universe, we say they're 3-dimensional, we know what that means. And then there's time. You can think of it, even before Einstein, we can think of time as a 4th dimension. If you want to define an event, something has happened, you have to say where it happened and when it happened, if you want to know everything about it. So there are sort of 4 numbers. The X, Y, and Z coordinates, these are the 3D coordinates that fix its position in space, then you have time. Well, Einstein said you can't separate space and time as a set of 3 numbers and 1 number. Time is almost like another axis. So you need to talk about 4-dimensional space-time. Now, we can't imagine what 4 dimensions looks like. Our brains are only 3-dimensional. And so what we do is throw away one of the dimensions of space. Imagine our space is flat. We're sort of cardboard cutout, flat picture on a screen. And so what I've got here is a block universe. It's a 3D block meant to signify the whole universe, the whole of space. But space is just this flat surface, because I've sort of thrown away the 3rd dimension, because then I can use it as a time axis. Okay? So that's the whole of space, and time creeps along for us along this axis. So you can imagine a cross-section through this universe, which is our now, this moment. And that now slice is moving along from left to right. Behind our now is the past, in front of us is the future, and a point on the now is our here and now. Okay? This is a very useful way of solving problems in physics, certainly where Einstein's theory of relativity becomes important. I'll say where we might want to use that. But what it suggests is something even more dramatic, even more bleak, in a way, than Newton's clockwork universe. Because in Newton's universe, you say, okay, the future's fixed, it's preordained, fate, as it were, but it hasn't happened there. It's yet to unfold, even if we could, in principle, predict what would unfold. In Einstein's block universe, the future is just as real as the past. Everything is frozen, static. What sort of view is... Well, we could never have this view of the universe. This is like a picture outside of space and time. This is the view that God has. Hurrah! I say that sometimes just in case, people say, oh, well, that would be the view that God has. So does this really mean that, the future is there, it's happening, that our present moment is no more special than any moment in the past, any moment in the future? Well, Einstein believed that. But it's a very extreme view to have. It's not really necessary to view all the future as fixed in this deterministic way. It does suggest that the future is predetermined, but it's not the whole story. We tend to use relativity theory. We do things we draw space-time diagrams, and we solve problems about different observers moving at different speeds relative to each other, and measuring time according to each of them. So those sort of tricks, this is like the block universe picture, but I've only got one distance axis and one time axis. For physicists, it's very useful. But for the rest of the world, we would like to know, what does it tell us about the nature of reality? You know, is there such a thing as fate? Am I really responsible for my actions? I mean, you know, does it matter if I think I'm doing something according to my own free will, am I really following just a preordained path into the future that I'd have been able to predict if I had a computer powerful enough? Well, the thing about Einstein's theory of relativity is that it gives us this new picture of time. It tells us something about how time flows. What Einstein discovered in 1905 is that as objects move close to the speed of light, strange things happen. So if you strap a clock to a rocket and have the rocket fly past at, say, 99% the speed of light, if you could track it as it goes by, you would see the clock ticking by the seconds more slowly than an identical clock that you have on Earth. Time is running slower on board the rocket. If you were on board the rocket, you could say, well, all motion is relative, relativity. And it's actually the Earth that's hurtling at 99% the speed of light in the opposite direction. And indeed, what you would see is the Earth clocks running slower. But this is more than just an optical illusion. Time really runs at different rates according to different observers, how fast they're moving. You can slow time down when you go very fast. This leads to something, a famous example in relativity theory called the twins paradox. The idea is that, you have two twins, and they're always, in physics, by the way, they're always called Alice and Bob. It's A and B, because physicists are very imaginative in that way. If ever you need a third observer, it's always Carol. So imagine Alice has the rocket, and she can fly off close to the speed of light and zip around the galaxy, whereas Bob's a bit of a coward, and he stays on Earth. If she travels close to the speed of light, and I don't want to get into the technical details here of the fact that, it should be a symmetric view one way or the other. This is an assignment I set to my undergraduate students to resolve. But, bear with me. If Alice travels around for what she would regard as 1 year, so she will have aged 1 year before she returns to Earth, the computer on board the rocket will tell her that 1 year has gone by. She feels perfectly normal. She doesn't feel her time has been going faster or slower. When she returns to Earth, she could find that 10 years have gone by on Earth. And Bob, her twin, is now 9 years older than her, because she's aged just 1 year. And there's nothing special about the 1 year and 10 years difference. It depends on how fast she's going, how close you can nudge towards closer to the speed of light. She could come back after just a week of travelling around, and 1,000 years, 1,000,000 years have gone by on Earth. By slowing time down, you see, this gives us a means of getting to the future. In a sense, this is time travel. So, is time travel possible? I can answer the first part of that question, because it turns out time travel into the future and into the past are two different things. Time travel into the future is possible. But it doesn't necessarily mean that the future is out there waiting for Alice, that the future's already sort of unfolded and she's getting to that future. All that's happening here is that she's moving out of Bob and Earth's time frame and fast forwarding to the future. She's getting to the future before everyone else. Less time has gone by for her. Now, you might argue, well, that's not so different to suspended animation, or you fall asleep and you think you've only been asleep for 10 minutes and 2 hours have gone by. But her time really has slowed down. She really has time travelled into the future. And this is not just some theory that some boffin, Einstein and others, have come up with. We know this happens. It's been proven time and time again. Experimenters back in the early 70s got 2 atomic clocks and synchronized them and put one on board an aircraft and flew it around the world and then compared them again. And they saw that there was a tiny difference. Now, the aircraft doesn't go anywhere near the speed of light, but the time difference was enough such that they could measure it. Tiny fractions of a second difference between them, and it agreed entirely with Einstein's theory of relativity. Now, I'm missing part of the story here because there's another way that we can slow time down. In 1915, Einstein completed an even greater theory, the general theory of relativity. So the first one, the 1905 one, was called the special theory. It was special because it was seen as sort of only part of the story, only part of this larger, more exotic theory. In general relativity, Einstein explains about how not only we have 4D space-time, but how space-time curves, and it curves due to gravity. So basically, he's done another one on Newton. Whereas Newton had this idea of space and time being separate, and Einstein said, no, they have to be combined. Now, he's attacked Newton's law of gravity. Newton was the guy sitting under the apple tree, and the apple falls on his head, and he thinks, things fall. Okay, people know that things fall. Newton, what he said was, there's this invisible force, like a rubber band that pulls all masses together. The apple falls to the Earth for the same reason that the Earth is kept in orbit around the Sun. Einstein went further. Einstein said that gravity is not, you don't have to think of it as an invisible force between objects. There's a deeper geometrical explanation. It's about how space-time, in fact, is curved. And, there are lots of examples in popular science books about space-time being like a sheet of rubber that has a dent in it where there's a mass and other objects roll into the dent. That's exactly the way objects move under the influence of a gravitational field. But what's interesting here is that what gravity also does is slow time down. In the same way that travelling close to the speed of light slows time down, so does gravity. And whereas when you travel close to the speed of light, there's always that sort of confusion. Well, hang on a minute, what's really slowing down? If Alice could say Bob went off, the Earth went off in the opposite direction and came back. Why is it Alice is the one whose clocks have run slower and she's gone to the future and not Bob? The technical detail is in the fact that Alice has had to speed up and slow down. She's simulating the effect of gravity. When you speed up, say on a plane about to take off on the runway, and you feel the G-force, G for gravity. Acceleration does the same thing as gravity. It slows time down, literally. So, here's a nice example. If my watch is running slow, as I'm sort of holding it down by my side, I could lift it up into the air so that it's slightly further away from Earth's gravitational pull, and that will speed it up. It would run a bit faster. Now, of course, in practice, I'd have to hold my arm up in the air for billions and billions of years, just to make up a second. It's probably more sensible to buy a new watch. But that really does happen. Time really, albeit for tiny fractions of seconds, time really will run slower the closer it is to the Earth. Time on the surface of the Sun runs slower than it does on the surface of the Earth, because the Sun's more massive. Time out in space, where there's no gravity, can run faster than it does on Earth. GPS satellites, anyone who's used GPS in their car or in their smartphone is making use of the fact that, we understand how time slows down. The satellites in orbit around the Earth have their clocks running slightly slower than ours because they're moving relative to us. But at the same time, their clocks should be running faster than ours because they don't feel gravity. They're in free fall around the Earth. And the computers that work out the time very accurately in order to locate positions on the surface of the Earth very accurately have to take into account the fact that you've got the satellite clocks running slower because of special relativity, the idea of get close to the speed of light and clocks run slower. But at the same time, they would run faster because of general relativity, because they're not feeling any gravity. And those two effects are in competition, but they don't cancel each other out. Which one wins depends on how high an orbit the satellite is, and hence how fast it's moving. You have to take this into account, otherwise we'd never be able to locate our positions to within the few meters that we've become accustomed to these days. Okay, so we can slow time down, we can travel into the future. We can slow time down through powerful gravitational fields, much more than we can on Earth. This is a famous picture of the Crab Nebula. It's a cloud of dust and gas thousands of light years away, but still in our galaxy. And this is the central heart of the nebula, and what you see, there's these two spots here. Ignore the one on the right, but the one on the left is the center of this nebula. It's actually the remnant of a supernova, a star that's run out of its nuclear fuel and exploded. And a lot of its material that's left over collapses under its own weight and forms this very dense object called a neutron star. Now, stars even bigger than the one that created the Crab Nebula, when they collapse, their gravity is so strong that they will collapse into a black hole. Black holes are simply dead stars, and they are predicted by Einstein's theory of relativity, even though at the time he didn't really believe they existed. Well, they do exist. We're almost certain of it. We see their signature out in space when we look through our telescopes. And they provide us with a possible means of building a time machine, which I'll come to at the end of my lecture. Okay. Determinism, the idea of the future being predetermined and preordained because of relativity, got a bit of a wake-up call in the 1920s. Quantum mechanics is the other great theory of 20th century physics. And whereas general relativity, Einstein's second theory, which describes essentially the whole universe, how gravity affects the nature of space and time itself, from general relativity grew out the field of cosmology and prediction of the Big Bang and so on. Quantum mechanics, on the other hand, is the theory of the very tiny, the theory of the subatomic world. And it's much weirder than relativity theory, believe me. It's to do with cats in boxes being dead and alive at the same time. My favourite picture of what quantum mechanics is about is the quantum skier. Ridiculous as far as we're concerned. There he is, he's fine, but somehow he's gone through past that tree on both sides. That's what things down at the quantum level really do. And no one has a common sense, sensible way of explaining how that happens. Well, I'm not going to talk about it. What I will say is that quantum mechanics rescues us from this bleak determinism, because down at the level of atoms, even something like when an atomic nucleus will radioactively decay, when it's going to spit out an alpha particle, is something subject to the laws of chance and probability. Statistically, if we have trillions and trillions of atoms, we can work out something called their half-life. How long does it take before half the atoms are going to spit out alpha particles and decay? But you look at one individual atom, and you can't tell. Not because our theories aren't clever enough, but because nature herself hasn't decided yet when this is going to happen. Quantum mechanics gives us back indeterminism. So our future is not decided. Oh, question mark, where it shouldn't be. Okay, even nature hasn't decided what's going to happen next. It means that even with the most powerful computers, once we have to take into account that down at the very basics, the building blocks, things haven't decided what's going to happen next, that means the future is open. It means we've rescued, in a sense, we've rescued free will. Different philosophers argue about whether this is actually true or not. The American philosopher Daniel Dennett, I think, would argue quantum mechanics doesn't rescue free will. So it's still actually a topic of debate. I mean, I don't want to make this sound as though 1920s quantum mechanics and suddenly, okay, we have free will, we are responsible for our actions. There is still a big discussion going on. Okay, so that's opened up the future, and I've said, well, we can travel to the future, but we're not really going to the future that's already there. We're just sort of getting there faster than everyone else. That's not real time travel. Real time travel is if we could go back to the past. And the same way we could say real time travel will be if someone from the future that pre-exists came back to visit us. They are traveling to their past. So, can we travel back in time? Well, as it happens, Einstein's general theory of relativity, the theory about gravity curving space-time and slowing time down and so on, the theory that predicts black holes, the theory that gave us the Big Bang, also tells us that, according to the maths, time travel into the past should also be possible. It allows it. Things called closed time-like curves. Despite that, most physicists, I think, if you asked certain and put money on it, they would say time travel into the past can't be possible. Not ruled out because their theories or the mathematics or the equations tell them, but because it doesn't make sense, because it leads to paradoxes. So what I'd like to do is give you two examples of time travel paradoxes, just to show you how weird, stupid things would be if we were really able to travel back in time. Now, that doesn't stop us from, enjoying time travel stories and films and so on, but let's try and force the paradox. Okay, I'm assuming most people in the audience are au fait with the Terminator films, but just in case, for those saddos who haven't seen any, I should point out you should, and I'll just quickly run you through the basic premise of the first of the Terminator films. Arnie here is the android from the future, sent to our time, 1980s, when the film was made, by the machines that rule the future. Now, the machines are in this battle against the rebel humans. The humans are led by John Connor. He's the good guy. Machines can't catch him in their time in the future, so they send the Terminator back to the past to kill John Connor's mother before she's given birth to him, because if she doesn't give birth to him, he would never have been born in the first place. They change the future. It's another take on what's famously called the grandfather paradox. Well, this being a Hollywood film, of course, Arnie fails to kill John Connor's mother, Linda Hamilton. This being a Hollywood film, John Connor sends his best mate back into the past to protect his mother. And if you remember the film, he does much better than protect her. He gets her pregnant, and she gives birth to John Connor. So his best mate is also his dad, and it's all very silly. But it's good fun. Okay, where's the paradox? Well, I'm going to force a paradox. What if, bear with me here, the machines do capture John Connor, but for some strange reason they decide not to kill him. They send him back in the past to kill his own mother. Okay, this is the take on the grandfather paradox. If you kill your own mother... In the original one, it's you have to kill your grandfather before he's met your grandmother, before she's given birth to your mother, before she's... And I've always wondered why you have to skip a generation, why you have to kill the male. Kill your own mother and be done with it. It's a cleaner scientific experiment. So, John Connor is given some kill-your-mother serum to brainwash him. And he goes back to the past and encounters his mother. What happens as he shoots her dead? Does he sort of fade out of existence? Does he suddenly disappear, that he was never there in the first place? She's dead. He was never born, so he wasn't there. This is the paradox, you see. Of course, the police come to investigate. Who is the murderer? Well, it wasn't John Connor. Perfect alibi. Never born in the first place. You can't argue with that. But of course, he was never born in the first place. He never would have grown up and gone back in time and killed her. So she survived and gave birth to him, and he grew up and he went back and killed her. So he wasn't born. So he didn't kill her. So he was born. And so on. Standard time travel paradox. Well, despite that, there are physicists, serious physicists, who work in relativity theory, who would argue that they trust the maths, and they say relativity theory says time travel into the past is possible. There must be a way out of the paradox. The quickest solution is to say that John can't kill his mother because there he is. Clearly he must fail in his attempt to kill her because she did give birth to him. There he is standing trying to kill her as proof that she gave birth to him. killing his mother would lead to what they would call an inconsistent solution. And that's his imaginative turn of phrase. But it's not very satisfying, is it? Again, it starts to play with this issue of free will. Why would John Connor fail to kill his mother? What if the machines pull him back to their time? Say, why did he fail? Well, they'd say, well, okay, maybe he comes to his senses at the last minute. Maybe the trigger on the gun gets stuck. Maybe he's just a lousy shot, and every time he shoots, his mother does a back somersault out of the way. And Linda Hamilton was pretty fit in that film, I should add. In both senses. So it doesn't matter. He must fail, because there he is. What if the machines pull him back, dose him up in kill your mother serum, extensive shooting lessons, lots of weapons that he can call upon? Is he going to fail every time he tries to kill her? Somehow, it's now in-your-face determinism. Whereas we talk about, is the future preordained and do we have free will? Well, now the future is fixed in the same way that the past is fixed, because they're linked together. He knows as he's trying to shoot her, well, I'm aiming it, but something's going to go wrong. I know it is, because clearly I must fail because I'm here. Well, there is another way of getting round the paradox. And in my mind, it's the only way that rescues the possibility of time travel into the past. And that is that our universe is not the only one. There are parallel universes. Now, there are plenty of reasons within modern physics to argue that parallel universes might exist. We have not a shred of evidence that they really do, but they're very handy. Parallel universes would remove what's called the anthropic problem, the anthropic principle, the fact that, everything has been so specially designed for us to be here. How could, all the laws of nature are tweaked perfectly for us to be here? Well, if there are parallel universes, then we just happen to be in the universe that was right for us to evolve in, and ask the question, how come we're here? There are many other universes where we didn't evolve. Parallel universes are very useful in explaining some of the weirdness of quantum mechanics. Here it helps us because it would suggest that when you travel back in time, you hook up your here and now to the past, inevitably that past will be not the past of your own universe. There are some very serious scientific papers looking into this. And so John Connor, when he travels back into the past, he slides into a parallel universe, one very similar to his own. In that universe, he can kill his mother. All that happens is that he would then never be born in that universe, while his own original mother carries on living healthily in the original universe. So parallel universes remove the paradox, as long as you buy into parallel universes. Let me give you another quick time travel paradox. The Mona Lisa paradox. Let's imagine Leonardo da Vinci has just finished his great work of art, and he's decided to take a break and pursue his other great love, which is science and inventing things. Let's say, along with all the pulleys and levers and screws and mechanisms he's invented, he's figured out how to build a time machine. And he hammers away in his shed, building a time machine. When it's finally complete, he goes to bed that night rather concerned about how he's going to test it out. Clever guy. He knows there are time travel paradoxes. Well, imagine he goes down to the shed the next morning, and to his surprise, he sees the time machine has been activated. In the pod is an item. Actually, it's a painting. And he quickly realizes this is a painting that's been sent to him from the future. It's a painting of a woman with the same facial bone structure as his Mona Lisa, the same long dark hair, but without her famous enigmatic smile. And he realizes quickly it's her ugly twin sister, Mona Lot, whom he's been avoiding having to paint for some time now, but he's got the sets, you see. And there's a note there from the future Leonardo saying, here, the painting of the Mona Lot, as proof that the time machine works. I sent this to you on such and such a day at such and such a time in the future. There are two paradoxes here. One of them is a bit like the Terminator paradox. You see, it's about the future being preordained. Leonardo da Vinci knows that one day he will become that future Leonardo da Vinci who put the painting in in the time capsule. What if he thinks, no, I want to keep it. I've got the set now, I'd like to keep both. What's the worst that can happen? Is a Time Lord going to come and say, you're going to rip the fabrics of space and time? You have to put it in. It's a paradox. He has to put it in because he does. The future is fixed. He does become that future Leonardo. Okay. I've sort of covered that in the last paradox. So let's say Leonardo da Vinci puts the Mona Lisa painting in the time machine, sends it back to the past at the allotted time, goes on into the future, quite relieved that he only has in his possession now the Mona Lisa painting, and that rather strange episode is in his past. There's still another paradox, you see. At a certain time in Leonardo da Vinci's life, he had in his possession the Mona Lisa painting. But at no point did he ever paint it. He found it in a time machine, kept it for a while, put it back in the time machine. Here's this wonderful work of art that's caught in a time loop that was never actually created at all. There's something called a Bilking Paradox. Again, the only way out of these paradoxes is to subscribe to this notion that parallel universes exist. Because then you could have two Leonardos. The Leonardo in the future who sends back the painting that he painted slides back to our Leonardo in our universe, and there he can keep it. Time travel into the past seems to require parallel realities. Otherwise, it leads to paradoxes that we can't explain. And yet, Einstein's general theory of relativity says nothing about parallel universes. But it does say that time travel into the past should be possible. Well, how would we go about building a time machine? The best current ideas go back to Carl Sagan's novel Contact, which is now, obviously some years ago, now made into a film starring Jodie Foster. Carl Sagan, being a practicing scientist himself, when he was writing the story of Contact about how he'd make contact with an alien civilization, he was looking for a means within physics to have a sort of a shortcut through space-time that didn't invoke some nonsense to do with dilithium crystals. And so he sent the manuscript to another physicist in California, Kip Thorne, who developed this idea of what we call a wormhole. See, Kip Thorne was an expert on black holes. And from what we know about black holes, the theory of black holes is that, they have an event horizon. Let's see, yes, okay. A black hole has an event horizon, which is the sort of the point of no return. If you get too close and you go beyond the event horizon, you're sucked in, and you go all the way down to the center, the singularity. A lot of work has gone into black hole research. We've seen signatures of black holes out in space because of the way they affect other stuff around them, like nearby stars or nearby debris and how it's sucked in. You don't see the black hole itself, of course, by definition. But we're not sure exactly what the inside of a black hole would look like. And it's not clear whether the inside of a black hole is a point, a singularity, so you fall in and get squashed down to zero size, or is it some sort of a gateway that would lead to a different space-time. So Kip Thorne played with this idea for Carl Sagan's story. He said if you could link two black holes and monkey around with the maths so that you remove the event horizons, so you allow it sort of a two-way travel and it's stable, you create what's called a traversable wormhole. Carl Sagan was very happy about this. He could use this idea for his story, and he did, as a means of short-circuiting two distant points in space. How does he do this? Well, we know, imagine our space is a sheet of paper. I'm throwing away one of the dimensions now. Shortest distance between 2 points is a straight line, A and B. But if you were able to bend the paper, you could imagine an even shorter distance between A and B that would involve jumping out of the paper. This is what we could imagine the curvature of our universe or our space-time could be like. Or just think of it as our space being curved. But we can't imagine it. We've got 2 dimensions here, and then when you curve the 2 dimensions, we can imagine it because that's turned it into curvature in a 3rd dimension. We can hold that picture in our heads. But take a volume and curve it, what does that mean? We can't. Okay, so it's like this, only 1 dimension more. And it gives us a shortcut. Well, Kip Thorne and his collaborators, soon after he had provided this advice to Carl Sagan for his novel, they realized that, of course, shortcuts in space should also mean shortcuts in time. So a wormhole wouldn't only join two different points in space, it should also be able to join two different points in time, and hence act as a time machine. Led to all sorts of wonderful stories and movies and programs about entering a wormhole or a stargate or whatever and going sort of from one universe to the other, or from one part of one universe to another part of the same universe, a different space and time, or just going back and forwards into the past. If time travel were possible, therefore, this is how we would make a time machine. Build a wormhole. Easy enough. Michio Kaku, the American physicist, has written about this, about how you would create a wormhole and how you would turn a wormhole into a time machine. I want to give you, just in case I haven't induced a headache completely, I see I have the countdown. Is that 8 minutes? Okay. I do want to give enough time for questions, so I'll go through this very quickly, so guaranteed to give you a headache. Remember Alice and Bob. Alice is the one who flies off in the rocket, close to the speed of light. She comes back to Earth. Less time has gone by for her. She's come back in the future. What if she and Bob both have one end of a wormhole? So this is what you'd see the wormhole mouth. The other mouth of the wormhole is out of our space, just like in the folded paper. The tube throat of the wormhole is not something in our space. So actually the other end of it is over in the rocket. That's where Alice is, in the rocket. He can see her through the wormhole shortcut. And of course she can see him from her end. If she were to travel around the galaxy close to the speed of light, when she comes back to Earth, let's say 1 year has gone by for her, 10 years has gone by for Bob, the wormhole is now provided a fixed tunnel between those two time frames. So it becomes a time machine that can take you backwards and forwards. He can go 9 years into the future, she can go 9 years into the past, if it's that way around. So you know, I've got confused now. So wormholes would allow the possibility of time travel into the past. Current scientific thinking is still not clear, A, on whether wormholes even exist in principle. Mathematically, we think they exist, but then mathematically we think time travel into the past is possible. No one knows whether there's a loophole in Einstein's theory of relativity that needs to be closed to rule out wormholes and time travel into the past. It would seem as though we are looking for a new theory, and a lot of physicists would say it's a theory of what's called quantum gravity. So it's linking together these two important ideas in 20th century physics. Quantum mechanics, the theory of the very small, and relativity, the theory of the very large. It seems if we were able to mesh those two together, we might be able to have a better understanding of the nature of time itself. Well, how close are we? I would argue not very close at all. Stephen Hawking thinks otherwise. He thinks we're very close to the final answer string theory or M theory. There's lots of other candidates. There's brain theory. There's loop quantum gravity. As far as I'm concerned, they're just clever mathematical tricks at the moment. A scientific theory is one that is testable. Scientific theory is one where we can do experiments to verify it or not. We don't even know what sorts of experiments, even though some physicists at the Large Hadron Collider think they may have a way of testing. I don't think it's clear yet whether we would know which of these is right, if indeed any of them are right. It would be nice to know in my lifetime whether time travel into the past is possible, whether parallel universes really exist or not, and answering some of those questions. In the meantime, we can enjoy time travel, stories, but whether we will ever be able to build a time machine, I think, is another matter entirely. Thank you very much. Thank you. And I see from the clock that's counting down, I have 5 minutes. So I'm happy to take questions for the next 5 minutes. Yes. I think you have to come to the microphone. Yes, sorry.
I think my head just exploded, but
Sorry.
wow. No, it's fantastic.
Good.
Given Occam's razor, that the simplest explanation is probably the best, if paradoxes lead us to assume that there must be, therefore, parallel universes, how about you can't travel back in time at all? Is that possibly the better theory than parallel universe?
Absolutely. I think that's probably, yeah. I'm trying to entertain you. I'm trying to open up the possibility that it might be possible. But actually, no, if push comes to shove, I would rather rule out time travel to the past along with parallel universes any day. Yeah.
Hi. That answer might make my question sort of invalid. I was just going to ask, if time travel to the past is possible, how would you answer like the Fermi paradox of time travel? You know, where are they?
Okay. So this is the idea that if time travel into the past is possible, then surely some future generation scientists will have figured out how to build a time machine, and they should have visited us and be among us today. Maybe that's what UFOs are. There are lots of ways of explaining that. First of all, it may well be that they're among us, but they just keep a low profile. Only the nutters see them. But actually, no. The proper answer is that if time travel into the past were possible, and you sort of hook up different times, you can only travel back. The earliest time you can travel back to is the moment the time machine is switched on. That's the earliest point in time that you can hook to. So you can't build a time machine that will take you back to the age of the dinosaurs. Now, if there was some naturally occurring time machine because of the weirdness of space-time from the early universe that's waiting out there for us to go through, maybe. But if you build a time machine tomorrow, the earliest we can ever travel back in time from the future is back to tomorrow. So if we don't see time travelers from the future, all that tells us is no one's built a time machine yet. Yeah.
Can I ask how you define a year? If I'm looking at Alice travelling around, I thought we define a year by the amount of time it takes the Earth to go around the Sun. So if the Earth has gone around the Sun 10 times, it has gone around the Sun 10 times. So surely Alice has just been away for a year for 10 years. How are you defining Alice's year?
What you do is you say there are different definitions of time according to your frame of reference. So if you're on Earth and not moving, that's a year. What Alice will see is, the time going by, and what she will see is the Earth going round the Sun much, much more, more slowly. Well, the whole solar system is zipping away from her. But if she could focus on the solar system as it moves away or towards her, she goes and comes back, she'll see the Earth going around the Sun much more slowly. She said, well, in my frame of reference now, the Earth has slowed down completely. So for her, 1 year has gone by, but on Earth, they will see her time slowing down. It's all down to your frame of reference. No one is right or wrong. We would argue, we're used to the Earth spending a year going around the Sun. That's what defines a year, and anything else be damned. But that's just from our perspective. You're not nodding very convinced. No. Well, listen, no, it's true. I mean, the idea of different perspectives about space and time is something that takes a while in a proper course on special relativity to understand. It's a bit like saying, look at a box and I see a side-on view and I see my face rectangular. You see my face all squashed up because of your perspective. We see shapes in space differently because of our different perspectives and points of view. Well, relativity is like that. Only you have to think about space and time altogether. If you're moving fast relative to each other, you see distances and times differently. So you'll see lengths shorter, and you see times differently. And it's only when you combine space and time together in this beautiful block universe that we can all agree it's a matter of perspective. But the math starts to get a bit more complicated. That's why so many people have published papers. I get the papers quite regularly, from nutters. It's very sweet. I have proved Einstein's theory of relativity wrong with nothing more than GCSE maths, and this is my 30 years of research, and it's just shit. I mean, the nicest phrase of one, he said, I have proved that reality is orthogonal to the speed of light. I keep them in a box, they're nice. So yeah, I mean, there is the explanation, but it's not one which is you could be readily convinced by just with a few sentences. I'm sorry. Yeah.
I think, unfortunately, we're out of time. That's going to be the last question. I'm so sorry.
Ask me later. I'm around. Oh, yeah. No, the last question's okay.
I think we're out of time.
Oh, we are out of time.
We're just
Sorry.
off, but there is a chance to ask later on. So
absolutely.
Have a nice round of applause, ladies and gentlemen, please. Very nicely done.
Thank you.